Look up on a clear, moonless night, far from the glare of city lights. You will see it, a faint, shimmering band of light, a celestial river, stretching across the immense, dark canopy of the heavens. Ancient civilizations saw it and wove it into their mythologies. The Greeks imagined it as the breast milk of a goddess, aporgalaxias kaiklos, or milky circle. From this ancient vision, our home in the cosmos received its name, the Milky Way. For millennia, this ethereal luminescence was a mystery, a beautiful but incomprehensible feature of our sky. We now understand it is not a celestial cloud, but a perspective trick. We are looking at our own city of stars from the inside, viewing its sprawling disk edge on from our humble suburban neighborhood. This is our galaxy, a self-contained island of stars, gas, and dust, one of hundreds of billions scattered throughout the observable universe. But it is ours. And its story is the grandest, most epic tale imaginable, a chronicle of creation, destruction, and cosmic evolution, written in the language of gravity and light. To truly grasp the scale of our galactic home is a profound challenge. Imagine our sun, the star that anchors our world, shrunk down to the size of a single grain of sand. On this scale, the nearest star, Proxima Centauri, would be another grain of sand over 4 miles away. The Milky Way galaxy, on this same scale, would be a swirling disk of sand grains larger than North America. It contains upwards of 400 billion stars, a stellar population so vast that if you were to count one every second, it would take you over 12,000 years to finish. This celestial metropolis is a barred spiral galaxy, a design of exquisite, spiraling elegance. At its heart lies a dense, glowing region known as the central bulge. This is the old city, crowded with ancient, reddish stars, some of which are nearly as old as the universe itself. They swarm in chaotic, elliptical orbits around the galactic core, a testament to the galaxy's primordial and violent formation. Imagine a glowing, elongated football of starlight, a swarm of celestial embers, from which the grander structure emerges. Extending from this central bar are the magnificent spiral arms, the galaxy's bustling, star-forming suburbs. These are not solid structures, like the spokes of a wheel. Rather, they are density waves, cosmic traffic jams, slow-moving ripples of higher gravity that sweep through the galactic disk. As clouds of gas and dust drift into these arms, they are compressed, squeezed by the increased gravitational pull. This compression triggers the collapse of vast nebulae, igniting them into the brilliant nurseries of new stars. Our own solar system resides within one of these arms, the Orion Cygnus arm, a minor spur nestled between two larger ones. We drift through this galactic neighborhood at a staggering velocity. Our sun, along with its entire planetary retinue, is hurtling through space at about 500,000 miles per hour, or roughly 230 kilometers per second. Even at this incredible speed, a single journey around the galactic center, one galactic year, takes our solar system approximately 230 million Earth years. This means the last time our planet was in this same cosmic position, dinosaurs were just beginning to dominate the terrestrial landscape. Humanity has existed for only a tiny fraction of a single galactic year. All of our history, our triumphs and our follies, has unfolded during a fleeting moment of this grand celestial orbit. The visible galaxy, this beautiful structure of stars and nebulae, is, astonishingly, only a tiny fraction of the whole. It is the luminous foam on the surface of a much deeper, unseen ocean. Surrounding the entire disk is a vast, spherical region called the halo, sparsely populated with ancient stars and globular clusters. But the halo's most significant component is something else entirely, something that betrays its presence only through its immense gravitational pull. This is the realm of dark matter. The mystery of dark matter began with an astronomical puzzle in the 1970s. The astronomer Vera Rubin was studying the rotation of galaxies. She expected to find that stars on the outer edges would move more slowly, than those closer to the bright, mass-rich center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. But her observations revealed something utterly perplexing. The stars on the galactic fringe were moving just as fast as those further in. This defied the laws of physics, unless there was a huge amount of unseen mass, a gravitational scaffold holding the galaxy together, preventing its rapidly spinning stars from flying off into the intergalactic void. This invisible substance, which we call dark matter, does not emit, absorb, or reflect any form of light. It is a ghost in the cosmic machine, accounting for over 80% of all matter in the universe. Our Milky Way is embedded within a colossal halo of this mysterious material, its gravitational influence shaping the galaxy's structure and destiny. We have built vast, subterranean detectors shielded from cosmic rays in a desperate attempt to catch a fleeting glimpse of a dark matter particle, but so far, this cosmic phantom has eluded all our traps. Its existence is one of the most profound and humbling truths in modern science, a constant reminder that the universe we can see is merely the tip of a much larger and stranger iceberg. Let us journey now to the very heart of our island universe, to the center of the galactic bulge, a place of extreme energies and cosmic violence. For decades, astronomers mapping the heavens with radio telescopes detected a powerful and compact radio source in the constellation of Sagittarius. They called it Sagittarius A star. As they watched the stars in its immediate vicinity, they saw them whipping around an unseen central point at mind-boggling speeds, some reaching millions of miles per hour. There was only one possible explanation for this celestial dance. At the precise gravitational center of the Milky Way lurks a monster, a supermassive black hole. This is not the kind of black hole formed from a single collapsing star. This is a leviathan, a gravitational singularity with the mass of more than 4 million of our suns, all compressed into a volume smaller than the orbit of Mercury. It is the ultimate anchor, the hub around which our entire galaxy revolves. It is a place where the laws of physics as we know them break down, where space-time is warped into an inescapable abyss. Its event horizon, the point of no return, is a boundary beyond which nothing, not even light, can escape. Yet, this heart of darkness is not merely a passive void, it is an active and dynamic engine. As gas clouds and unfortunate stars venture too close, they are ensnared by its ferocious gravity and torn apart. The resulting debris forms a swirling, superheated accretion disk, a maelstrom of matter spiraling towards its doom. This disk glows with incredible intensity across the electromagnetic spectrum, from radio waves to X-rays, making the galactic center one of the brightest and most energetic places in our cosmic home. We are fortunate to be located a safe 26,000 light-years away, far from the fury of this central engine, able to observe its magnificent power from a tranquil distance. Our galaxy is not a static, unchanging entity. It is a dynamic ecosystem, constantly recycling material and giving birth to new generations of stars. The spiral arms are the epicenters of this cosmic creation. Here, we find vast ethereal clouds of gas and dust, known as molecular clouds or stellar nurseries. These nebulae are breathtakingly beautiful, cosmic canvases, painted with the light of the young stars igniting within them. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one such local star-forming region. Inside its glowing folds, gravity is slowly but inexorably pulling knots of gas together, compressing them until their cores become hot and dense enough to trigger nuclear fusion. At that moment, a new star is born, a new point of light in the galactic tapestry. These young, massive stars are brilliant but short-lived. They burn through their nuclear fuel with reckless abandon, shining with a fierce blue-white intensity for a few million years before meeting a spectacular demise. They explode as supernovae, cataclysmic events that can briefly outshine the entire galaxy. These explosions are not just endings, they are also beginnings. They forge the heavier elements, the carbon in our bodies, the oxygen we breathe, the iron in our blood, and blast them out into interstellar space. This stardust then seeds the next generation of molecular clouds, enriching them with the raw materials necessary for forming planets, and perhaps life itself. We are, in the most literal sense, made of star stuff, forged in the hearts of long-dead luminaries, and recycled through the grand cosmic ecosystem of the Milky Way. The life of a galaxy is not a solitary affair. Our Milky Way is the dominant member of a small cluster of galaxies, known as the local group. It is a cosmic neighborhood containing over 50 galaxies, most of which are small, faint dwarf galaxies. And our home galaxy has a dark secret. It is a cannibal. Throughout its 13 billion year history, the Milky Way has grown to its current size by consuming, merging with, and tearing apart countless smaller galaxies. The evidence of this galactic violence is written in the stars. Astronomers have discovered vast streams of stars in the galactic halo, long, flowing rivers that follow peculiar orbits. These are the ghostly remains of dwarf galaxies that strayed too close, their stellar populations ripped from them by our galaxy's powerful tides, leaving behind cosmic breadcrumb trails that map their final, agonizing journeys. The Sagittarius dwarf galaxy is currently in the process of being devoured, its structure being unraveled as it passes through our galactic disk. This process of cosmic consolidation is far from over. Our largest neighbor in the local group is the Andromeda Galaxy, another majestic spiral even larger than our own, and it is hurtling towards us at a speed of nearly 70 miles per second. Every second, we are about 250,000 miles closer. Currently separated by 2.5 million light-years, our two galaxies are locked in an inexorable gravitational dance that will culminate in a cataclysmic collision. In about 4.5 billion years, the skies of a future Earth will be filled with the breathtaking spectacle of Andromeda's spiral, growing ever larger until it dominates the celestial sphere. The ensuing merger will be a slow-motion cosmic ballet, lasting hundreds of millions of years. The galaxies will pass through each other like ghosts, as the distances between individual stars are so vast that direct stellar collisions will be exceptionally rare. However, the powerful gravitational forces will warp and distort both galaxies, flinging out enormous tidal tails of stars and gas. The central supermassive black holes will eventually find each other, spiraling inward in a deadly embrace that will unleash tremendous bursts of gravitational waves. The vast clouds of gas from both galaxies will collide and compress, triggering a galaxy-wide starburst, a furious wave of star formation that will set the newly merged galaxy ablaze with light. The final result will be a single, gigantic elliptical galaxy, a new entity that some astronomers have already nicknamed Milkomeda. Our familiar spiral home will be gone, transformed into something new and unrecognizable. Beyond the stars and nebulae, our galaxy is also home to some of the most exotic and extreme objects in the universe. When a massive star dies in a supernova, its core can collapse under its own immense gravity, crushing matter to an unbelievable density. If the core is massive enough, it forms a black hole, but if it falls just short of that threshold, it becomes a neutron star. These are city-sized spheres so dense that a single teaspoon of their material would weigh billions of tons on Earth. They are essentially giant atomic nuclei, composed almost entirely of neutrons. Some neutron stars spin at incredible rates, hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. As they rotate, they sweep beams of radiation across space, like a celestial lighthouse. If one of these beams happens to be pointed towards Earth, our radio telescopes detect a precise, repeating pulse. These objects are known as pulsars. The first one was discovered in 1967 by Jocelyn Bell Burnell, and for a time, the regularity of its signal led to speculation that it could be a beacon from an extraterrestrial civilization. We now know them to be natural, if extraordinary, cosmic clocks. Others, called magnetars, have magnetic fields so powerful they can buckle the star's surface, causing starquakes that release colossal bursts of gamma rays, the most energetic form of light. The Milky Way is also a graveyard. For every bright, shining star we see, there are the cold, dark remnants of those that have exhausted their fuel. Stars like our Sun will end their lives not as supernovae, but by gently shedding their outer layers to form a beautiful, glowing planetary nebula. Left behind at the center will be a white dwarf, the hot, dense, Earth-sized core of the former star. With no fuel left to burn, these stellar embers will simply cool and fade over trillions of years, eventually becoming cold, dark objects known as black dwarfs, silently drifting through the eternal night. Our galaxy is slowly filling up with these stellar ghosts, the quiet final chapter in the life stories of countless suns. But perhaps the most profound fact about our galaxy is not its size, its black hole, or its violent future. It is the sheer, unadulterated potential it holds. Our Sun is just one of hundreds of billions of stars, and we now know that planets are not the exception, but the rule. Missions like the Kepler Space Telescope have revealed that most stars in the Milky Way likely host planetary systems. Statistical estimates suggest that there could be tens of billions of Earth-sized planets orbiting within the habitable zones of their stars, the temperate region where liquid water could potentially exist on a planet's surface. Think of it. Billions of worlds with the potential for liquid oceans, atmospheres, and the basic ingredients for life. Our galaxy is a vast cosmic laboratory running billions of simultaneous experiments in planetary formation and, possibly, biology. This realization has transformed our perspective. We are no longer just looking at points of light in the sky. We are looking at potential solar systems, each with its own unique story, each a potential home for life. It forces us to confront one of the deepest questions we can ask. Are we alone? This question gives rise to the famous Fermi paradox. Given the immense number of stars and potentially habitable planets in our galaxy, and the vast amount of time it has existed, it seems statistically probable that other, intelligent, technological civilizations should have arisen. Some of these could be millions or even billions of years more advanced than us. So, where is everybody? Why is the cosmos so quiet? There are many potential solutions to this silence. Perhaps intelligent life is incredibly rare. Perhaps the vast distances between stars make contact impossible. Or perhaps there is a more sobering answer, that civilizations, once they reach a certain technological level, inevitably destroy themselves. The silence of the galaxy could be a warning. The search for an answer continues. We scan the skies with radio telescopes, listening for a signal, a single, unambiguous whisper from another intelligence that would forever change humanity's place in the cosmos. We are cataloguing the atmospheres of distant exoplanets, searching for the chemical fingerprints of biological activity. Every new discovery about our galaxy adds another piece to this grand puzzle. The structure of our home provides a blueprint for what a typical galaxy looks like, informing our search for life-bearing environments. The violent history of our galaxy reminds us that the universe is not always a placid place, and that planetary systems must survive cosmic radiation, nearby supernovae, and gravitational perturbations to flourish. Our understanding of the Milky Way is itself a testament to human ingenuity. It is a story of patient observation, of brilliant deduction, and of technological prowess. It began with Galileo turning his rudimentary telescope to that milky band, and resolving it, for the first time, into countless individual stars. It continued with astronomers like William Herschel attempting to map its structure by painstakingly counting stars in different directions, mistakenly placing our solar system near the center. The breakthrough came in the early 20th century, with Harlow Shapley's study of globular clusters, the ancient swarms of stars in the halo. He noticed they were not centered around us, but around a distant point in the direction of Sagittarius, correctly deducing that this was the true galactic center and that we were located far out in the galactic suburbs. Then came Edwin Hubble, who proved that the spiral nebulae, like Andromeda, were not clouds within our own galaxy, but were in fact distant island universes in their own right, galaxies just like our Milky Way. This single discovery expanded the known universe by an unimaginable factor, transforming our galaxy from being the entirety of creation to being just one of billions. Each of these revelations was a step in a journey of cosmic humility, a process of steadily removing humanity from the center of things, first from the center of the solar system, then from the center of the galaxy, and finally from any special place in the universe at all. Even the very name of our galaxy, the Milky Way, only refers to the band of light we see in our sky. Technically, the celestial body itself is known as the galaxy, with a capital G. When we speak of other galaxies, we use a lowercase g. This linguistic quirk is a holdover from the time when we believed ours was the only one in existence. It is a small, subtle reminder of how far our knowledge has come. The galaxy's disk is not perfectly flat. It is warped like a vinyl record, left out in the sun. The edges on one side are bent upwards, and on the other, downwards. This warping is likely the gravitational legacy of past interactions. With satellite galaxies, their gravitational tugging twisting the shape of our galactic home over billions of years. The galaxy is also not silent. While space is a vacuum and cannot carry sound waves in the conventional sense, the universe is awash in a different kind of music, radio waves. If we could translate these radio frequencies into audible sound, the galaxy would be a roaring, hissing, cacophonous place. We would hear the static crackle of star-forming regions, the steady, rhythmic beat of pulsars, and the deep, powerful hum from the accretion disk around our central black hole. It is a cosmic symphony, playing out on an unimaginable scale, and our radio telescopes are the ears with which we listen to it. Even the space between the stars is not truly empty. It is filled with the interstellar medium, a tenuous mixture of gas, dust, cosmic rays, and magnetic fields. Though its density is far lower than any vacuum we can create on Earth, over the vast distances of the galaxy, it adds up. This medium is the raw material for future stars, but it also acts as a cosmic fog, obscuring our view of the galactic center in visible light. That is why astronomers must rely on infrared, radio, and X-ray telescopes to peer through the veil of dust and study the secrets hidden at our galaxy's core. This galactic dust is composed of tiny grains of silicates and carbon, the very same materials that form rocky planets like our own. Our journey through the Milky Way reveals a place of breathtaking beauty, unimaginable scale, and profound mystery. It is a dynamic, evolving system, a celestial engine of creation and destruction. It is a cannibal and a creator, a graveyard and a cradle. It is a structure held together by an invisible phantom, anchored by a monster, and filled with billions of worlds of untold potential. Every star is a sun, every point of light is a potential solar system, and we are a part of it. We are not just living in the galaxy is living in us. The atoms that make up our bodies were forged in the hearts of its stars. The water in our oceans was delivered by comets formed in its protoplanetary disk. Our planet was born from its dust, and our lives are governed by the light of one of its average, unassuming stars. To study the Milky Way is to study our own origin story on the grandest possible scale. It is to read a history book written in the light of ancient stars and in the gravitational echoes of cosmic collisions. It is to look at the night sky not as a random scattering of lights, but as a deep, intricate, and interconnected structure, our home, our city, our universe. The faint, milky band that has inspired awe and wonder for all of human history is an invitation. It is an invitation to explore, to question, and to understand our place within this vast and magnificent cosmic tapestry. And we have only just begun to read its first pages. The journey ahead is long, and the secrets yet to be uncovered are surely even more incredible than anything we have learned so far. The Milky Way awaits. What if the most important feature of our cosmic home isn't a thing at all? For millennia we have looked to the heavens and seen a story of presence, a grand narrative written in light. We charted the wandering planets, connected the stars into heroes and monsters, and later, through the unflinching gaze of our telescopes, we uncovered a universe overflowing with creation. We saw nebulae where new suns were being forged from incandescent dust, and we found galaxies, those sprawling cities of starlight marching in their billions toward a horizon we can never reach. Our science, our philosophy, our very sense of place became rooted in this magnificent plenitude. We are adrift in a sea of brilliance, a cosmos so densely packed with wonders that 1,000 lifetimes would not be enough to witness them all. This is the universe we were taught to see, the one we celebrate in breathtaking photographs from orbit. And yet this vision, as beautiful as it is a profound and spectacular illusion. It's a trick of perspective, a comforting story we tell ourselves while standing on a shore, mistaking the crashing waves for the true nature of an impossibly deep ocean. The most staggering truth about the cosmos isn't what's there, but what isn't. The great secret hidden in plain sight is that the universe is defined not by its dazzling islands of matter, but by the colossal, soul-crushingly vast oceans of nearly nothing that lie between them. We have spent centuries mapping the light, but the time has come to map the darkness, because it is in the cartography of absence, in the architecture of the void, that the real story of our cosmic address is finally being told. And it begins with a chilling revelation. Our own galaxy, the Milky Way, exists on the edge of a precipice, a shore that borders an abyss of almost unimaginable scale. An emptiness that has been shaping our destiny for billions of years without us ever knowing its name. To understand this emptiness, we first have to appreciate the structure it stands in contrast to. When we zoom out from our local star system far beyond the familiar planets and the Kuiper belt past the ghostly Oort cloud that encircles our sun, the universe begins to organize itself. Individual galaxies like our own start to look less like isolated islands and more like shimmering beads on an invisible string. This is the first glimpse of the cosmic web, the largest known structure in existence. It is the luminous skeleton of the universe, a filigree of unimaginable proportions sculpted by the one force that governs the cosmos on its grandest scale, gravity. For more than 13 billion years, gravity has been patiently at work playing a game of cosmic aggregation. It began in the primordial soup of the early universe, where tiny, almost imperceptible fluctuations in density acted as seeds. Regions that were infinitesimally denser than their surroundings began to pull more matter in a process that over eons snowballed into a magnificent and complex architecture. The scaffolding for this entire structure is a substance we cannot see, a ghostly material that outweighs all the stars and gas we can detect by a factor of 5 to 1. We call it dark matter. It is the invisible architect, the silent puppeteer, forming a vast, interconnected network of filaments and clumps that stretches across billions of light years. The galaxies we see, the glowing matter of the cosmos, are merely the luminous paint tracing the contours of this unseen framework. These filaments of the cosmic web are the great transportation highways of the universe. They are rivers of dark matter, and flowing along them are the galaxies themselves, pulled by the relentless current of gravity toward even denser regions. Where these filaments intersect, they create cosmic metropolises, vast and brilliant galactic clusters. These are the busiest, most chaotic places in the universe, cauldrons of gravitational violence, where thousands of galaxies are drawn together, colliding, merging, and being torn apart in a celestial ballet that spans hundreds of millions of years. These clusters are the great nodes of the web, shining with the combined light of trillions of stars and glowing in the X-ray spectrum from the superheated gas that fills the space between them. Surrounding these nodes are the galactic walls, enormous flattened sheets of galaxies that can stretch for hundreds of millions of light years, forming the boundaries of even larger structures. If you could see it all at once, this cosmic web would resemble a sponge or perhaps the intricate neural network of a brain. It is a structure of breathtaking complexity and beauty, a universe woven together from threads of shimmering light and invisible matter. For a long time, we assumed our place within this grand tapestry was unremarkable, that the Milky Way was just one more galaxy among countless others, nestled comfortably within a typical filament part of the universal hum of existence. But the maps we began to build in the late 20th century told a different story. As we surveyed the heavens, plotting the positions of tens of thousands of galaxies, a strange and unsettling pattern began to emerge. In one direction, looking out from our galactic home, the tapestry seemed to have a hole in it. The brilliant threads of the cosmic web appeared to fray, the shimmering walls of galaxies fell away, and the universe in that specific patch of sky grew unnervingly quiet. This is the frontier of cosmic cartography, where astronomers become explorers of the great voids. These are not pockets of absolute nothingness. The vacuum of a void is no more perfect than the vacuum of deep space within our own galaxy. Instead, they are regions of profound underdensity, the cosmic deserts that were left behind as gravity herded matter into the filaments and clusters. Imagine the universe as a collection of soap bubbles. The luminous galaxies and clusters would trace the surfaces where the bubbles meet, forming a network of bright walls and junctions. The voids are the vast, dark interiors of the bubbles themselves. They are the echoes of creation's initial roar, preserved regions of space that have evolved in quiet isolation, shielded from the gravitational chaos that defines the rest of the cosmos. Their scale is almost beyond human comprehension. A typical void can be 100 million light-years across a volume so immense that thousands of galaxies like our Milky Way could fit inside and still be lost. But within these colossal spheres, there is almost nothing. You could travel for 50 million light-years in a straight line, and perhaps encounter only a handful of small, lonely, and unusually pristine galaxies, celestial castaways that have somehow managed to evolve in the profound quiet. The light from one end of a large void takes longer to cross it than the entire age of the dinosaurs on Earth. These are the true deserts of the universe, places where the cosmic web has been stretched so thin it has effectively vanished. The formation of these voids is a story of gravitational exodus. In the early universe, the regions that would become voids started out just slightly less dense than average. While their denser neighbours were pulling in matter, these regions were doing the opposite. The matter within them was being pulled away, evacuated by the gravitational lure of the burgeoning walls and filaments surrounding them. It was a cosmic sorting process on the grandest of scales. Matter flowed out of the voids and into the web, like water draining from a vast, shallow basin into a network of deepening rivers. This process left behind immense chasms of expanding space, dominated not by the gravitational pull of matter, but by the mysterious push of dark energy, the force that is accelerating the expansion of the universe itself. Inside a void, this cosmic acceleration is felt more keenly. The few galaxies that reside there are being pushed apart from each other even faster than galaxies in the cosmic web. They are islands in an ever-expanding ocean of emptiness. Studying them is like finding a pristine fossil, a glimpse into what the universe was like before the rough and tumble evolution of dense clusters transformed galaxies. They are quiet, gentle places where star formation proceeds slowly and galactic mergers are almost unheard of. But for all their apparent serenity, the voids are not passive structures. They are not merely empty spaces on the map. Their very existence, their sheer gravitational absence, exerts a subtle but powerful influence on the cosmos around them. An absence, it turns out, can have as much gravitational power as a presence. A mountain pulls you toward it, but a deep valley, by its lack of mass, effectively pushes you away. Voids act as cosmic-scale valleys in the fabric of space-time, repelling galaxies that lie near their edges. And this brings us back home to our own small corner of the cosmos. For decades, astronomers have been puzzled by the motion of our local group of galaxies, which includes the Milky Way and Andromeda. We are hurtling through space at a staggering 600 kilometers per second, a velocity that could take you from Los Angeles to New York in less than 7 seconds. Part of this motion is explained by the gravitational pull of nearby structures like the massive Virgo cluster and the even larger Shapley supercluster, a truly colossal congregation of galaxies that acts as a great attractor. We are being pulled toward this immense concentration of mass. But the numbers never quite added up. The pull from the attractors we could see wasn't strong enough to fully account for our tremendous speed. There was a missing piece of the puzzle, a force that was unaccounted for. The answer, it turned out, was not another pull but a push from behind. As we mapped the universe in ever greater detail, the shape of the void next door began to resolve itself. It was not just a simple void, but a supervoid, a vast composite of smaller voids that together form one of the most significant underdense regions in our observable vicinity. It sits squarely in the northern celestial hemisphere, looming directly above the plane of our Milky Way. We call it, with a chillingly simple name, the Northern Local Supervoid. This is the great emptiness that defines our cosmic neighborhood. It is a chasm of space-time, nearly 1 billion light-years in diameter, a region where the density of matter is far, far below the cosmic average. Our Milky Way galaxy lies on its southern shore like a coastal city perched on the edge of a continent-sized desert. The Shapley supercluster and other attractors are pulling us forward, yes, but the northern local supervoid is simultaneously pushing us from behind. Its profound lack of mass creates a gravitational differential, a cosmic slope down which our entire local group is sliding. This colossal unseen structure is the missing component of our motion, the ghost in the machine that has been dictating the course of our galactic journey for eons. Its discovery has fundamentally rewritten our understanding of our place in the universe. We are not simply residents of the cosmic web. We are refugees fleeing the edge of an immense emptiness. This raises a cascade of profound and tantalizing questions. How did this supervoid form with such proximity to a relatively dense region like our own? What secrets do the few isolated galaxies stranded within its depths hold about the evolution of the universe? Has its presence influenced the very formation and structure of the Milky Way itself, shaping the stream of satellite galaxies that orbit us? And as we continue our high-speed journey away from it, what does our future trajectory look like? We are beginning a journey not into the light, but into the deepest shadows of the cosmos. We are setting sail across the silent, dark ocean that begins at our own doorstep to explore the nature of the great celestial abyss, the emptiness above us, and to understand how the story of nothing is in fact the story of everything. What is a map? At its heart, it is a declaration, a statement of courage against the vast, unnerving unknown. For millennia, we have drawn lines on parchment and pixel to tame the wilderness, to give names to the nameless, and to shrink the terrifying scale of the world down to something we can hold in our hands. On the edges of these early maps, where knowledge failed and imagination took hold, cartographers would write a warning times, hic sunt dracones *, here be dragons. It was an admission of ignorance, a boundary marker for the known world. We believed for a time that we had finally slain those dragons, charting every continent, sounding every ocean trench. We thought we had completed the map. We were wrong. We had merely been mapping a single room while the true incomprehensible mansion of the cosmos waited just outside the door, its scale and its secrets utterly beyond our conception. Our earliest celestial maps were beautiful, but they were profoundly mistaken. They were maps of a comfortable human-sized universe. The stars, those pinpricks of light in the velvet dark, were seen as fixed points on a crystalline sphere, a majestic but ultimately static ceiling above our world. They were scenery, not destinations. Even as our telescopes grew more powerful through the 17th and 18th centuries, revealing smudges and faint ghostly swirls of light nestled among the stars, our perspective remained stubbornly local. French astronomer Charles Messier, hunting for comets, catalogued over 100 of these fuzzy objects to avoid mistaking them for his true quarry. To him, they were annoyances, celestial smudges on the lens of his telescope. He meticulously recorded their positions, creating a catalogue of cosmic nuisances. What he was unwittingly doing was drawing the first crude sketches of a coastline he could not possibly comprehend, charting the shores of an ocean of existence whose existence he never suspected. His M31, the Andromeda Nebula, was just another faint patch, a curious but contained anomaly within the grand solitary kingdom of our own Milky Way. This was the prevailing view for centuries, that everything we could see was part of one colossal city of stars. Our galaxy was the universe. There was nothing else. The debate that simmered in the early 20th century was not about whether other galaxies existed, but whether these spiral nebulae were merely nascent solar systems forming within our own or distant, separate but still subordinate clouds of gas. The argument was a clash of titans, astronomers like Harlow Shapley arguing for a single grand Milky Way and Heber Curtis championing the radical island universe's hypothesis. It was a debate about the very size of creation fought with blurry photographic plates and fiercely defended calculations. But without a reliable way to measure the distance to these ethereal objects, the argument remained a stalemate, a philosophical deadlock at the heart of astronomy. The dragons of the unknown still circled just beyond the reach of our instruments. The key, the weapon that would finally slay them, was hidden within the stars themselves. It required a new kind of vision, a new kind of observatory, and a man whose patient, meticulous gaze would forever redraw the map of everything. His name was Edwin Hubble. Perched high above the shimmering lights of Pasadena at the Mount Wilson Observatory, he commanded the most powerful telescope on Earth, the 100-inch hooker. Night after frigid night, he guided the colossal instrument, capturing the faint ancient light from the Andromeda Nebula onto delicate glass photographic plates. He wasn't just looking, he was hunting. He was searching for a specific type of star, a cosmic metronome known as a Cepheid variable. These remarkable stars pulse, brightening and dimming with a precise, unwavering rhythm. And crucially, as discovered by Henrietta Swan Leavitt, the speed of that pulse is directly linked to the star's true intrinsic brightness. They are the standard candles of the cosmos. If you can find one, you can measure its pulse, determine its true wattage, and by comparing that to how dim it appears from Earth, you can calculate its distance with astonishing precision. It is the most elegant and powerful yardstick the universe has ever provided. For years, Hubble searched. The work was grueling, a painstaking comparison of photographic plates exposed for hours, hoping to catch a single telltale flicker in a sea of billions of stars. Then on the 6th of October 1923, he found one. On a plate designated H335H, he identified a single pulsating point of light within a spiral arm of Andromeda. He crossed out his initial notation of N for nebula, and in a moment of world-altering revelation scrawled in bold letters VAR, he had found his variable star. He tracked its pulse, he did the calculations, and the number that emerged was not merely large, it was revolutionary. It was a figure so immense it shattered the very foundations of astronomy. The Cepheid, and by extension the Andromeda Nebula, was not a few thousand light-years away, nestled comfortably within the Milky Way's borders. It was nearly 1 million light-years distant, a staggering, almost blasphemous distance that placed it far, far outside our own galaxy. In that single moment, with one observation, the known universe did not just double or triple in size, it exploded. The M31 Nebula was not a cloud of gas. It was the Andromeda Galaxy, a majestic spiral metropolis of stars, a sister city to our own Milky Way, every bit as vast and complex. And if Andromeda was a galaxy, then all the other faint smudges Messier had catalogued were galaxies too. Tens, hundreds, thousands of them. The universe had been blown open. We were not the sole occupants of a cosmic kingdom. We were residents of one island in a limitless archipelago, a potentially infinite scattering of island universes across an ocean of space-time. Hubble had not just discovered another galaxy, he had discovered the rest of the universe. The map didn't just need to be redrawn, the very paper it was printed on had to be thrown away, replaced by something of an infinite, terrifying and exhilarating new dimension. This was the first great cartographic revolution, the moment our perception of home expanded from a single island to a boundless sea dotted with countless others. But this static map of islands, however vast, was still incomplete. A new mystery was already emerging, one that would reveal that this cosmic ocean was not still, but was in fact a raging, expanding torrent. Even before Hubble's paradigm-shifting discovery, an astronomer named Vesto Slipher at the Lowell Observatory in Arizona had been patiently studying the light from these spiral nebulae. He was performing spectroscopy, splitting their faint light into its constituent colors, a rainbow barcode that reveals a celestial object's chemical makeup temperature and, most importantly, its motion. He expected to find a random assortment of motions, some nebulae moving towards us, some away, some orbiting each other, a chaotic dance within our Milky Way. But what he found was deeply puzzling, a result so strange it bordered on the unbelievable. Of the dozens of nebulae he studied, nearly all of them were screaming away from us at incredible speeds. Their light was stretched, its wavelength shifted towards the red end of the spectrum, a phenomenon known as redshift. It was the cosmic equivalent of a siren's wail lowering in pitch as an ambulance speeds away from you. But why? Why was almost everything in the universe seemingly desperate to get away from us? It was a profound cosmic rejection that made no logical sense in a static universe. It was Hubble who provided the second devastating blow to the old cosmology. By combining Slipher's redshift data with his own new painstakingly calculated distances to these galaxies, he uncovered a stunning and profoundly simple relationship. The farther away a galaxy was, the faster it was receding from us. This wasn't a random scattering. It was an ordered, elegant, and universal law. This discovery, now known as Hubble's law, was the definitive proof that our universe is not a static collection of islands in a calm sea. It is a dynamic, evolving entity. It is expanding. And the motion of these galaxies is not like shrapnel flying through a pre-existing space from a central explosion. Rather, it is the very fabric of space-time itself that is stretching, carrying the galaxies along with it for the ride. Every point is moving away from every other point. An observer in any galaxy would see the exact same thing, a universe of galaxies rushing away from them in all directions. There is no center to this expansion, or rather, everywhere is the center. This revelation gave astronomers their second revolutionary map-making tool. If a galaxy's redshift is directly proportional to its distance, then suddenly the arduous task of finding standard candles became unnecessary for creating a broad brush map of the cosmos. Astronomers could now simply take a spectrum of a distant galaxy, measure its redshift, and instantly know its approximate distance. It was like inventing a cosmic GPS. The floodgates of cosmic cartography were thrown open. For the first time, we could begin to plot the universe not as a flat two-dimensional projection on the sky, but in 3 dimensions. We could chart its depth. We could finally begin to draw the true architecture of reality, to map the locations of thousands and then millions of galaxies. And as the first truly 3-dimensional maps began to take shape in the 1,970 seconds and 80 seconds, they revealed a structure more intricate, more unexpected, and more strangely organized than anyone had ever dared to imagine. The galaxies were not scattered randomly like dust motes in a sunbeam. They were arranged in a breathtaking, colossal pattern. The pioneers of this new cartography, astronomers like Margaret Geller, John Hutra, and Valérie de la Parente, embarked on monumental survey projects. They spent years pointing telescopes at slice after slice of the sky, meticulously capturing the light from one faint galaxy after another, measuring its redshift and adding its position to a growing 3-dimensional digital proof model. It was pointillism on a cosmic scale, and as the points accumulated, a ghostly image began to emerge from the static. It was a vast, interconnected lattice of matter, a luminous and delicate filigree stretching for hundreds of millions of light-years. They called it the cosmic web. It was a universe organized into immense flattened sheets of galaxies known as walls, and long twisting tendrils of matter called filaments. Where these filaments and walls intersected, they formed dense, gravitationally bound knots, the great superclusters, sprawling metropolises containing thousands of galaxies glittering with the light of trillions of suns. In 1989, Geller and Hutra unveiled the Great Wall, a staggering sheet of galaxies stretching more than 500 million light-years across the sky, the largest single coherent structure ever seen. It was a triumphant moment, a confirmation that the universe, for all its chaos, possessed a deep, underlying and majestic order. But in discovering this spectacular web of light, humanity had inadvertently discovered something else, something far larger and far more unsettling. For the cosmic web, by its very nature, defines its opposite. The filaments, walls, and clusters, for all their grandeur, make up only a tiny fraction of the volume of the universe. In between these luminous structures were vast, dark, and astonishingly empty regions. These were the cosmic voids. They are not merely empty patches of space. They are the fundamental building blocks of the cosmic structure, immense gravitational deserts, some stretching for hundreds of millions of light years, almost entirely devoid of galaxies, stars, or even dark matter. As the maps grew more complete, the sheer scale of these voids became terrifyingly apparent. They were the blank spaces on the new map of the cosmos. And on the edges of these spaces, where the knowledge of our surveys faded into the unobserved dark, the modern astronomer could once again feel the primal urge to write, "Here be dragons." For decades, this grand structure was something that happened out there. It was a feature of the distant universe, a grand but remote architecture that we observed from a safe and presumably typical vantage point. Our own cosmic neighborhood, the local group of galaxies containing our Milky Way Andromeda and a few dozen smaller dwarf galaxies, seemed to be located in a fairly average, unexceptional part of a filament. But as our measurements became more precise, a subtle and persistent anomaly began to trouble the astronomers who studied our local cosmic flow. The Milky Way is not just moving away from distant galaxies as part of the overall Hubble expansion. It has its own peculiar velocity and extra motion on top of the cosmic flow. We and our entire local group are hurtling through space at over 600 kilometers per second, that's over 2 million kilometers per hour, towards a distant region of space in the direction of the constellations Hydra and Centaurus. For years, the cause was presumed to be the gravitational pull of nearby massive structures like the Virgo supercluster and a more distant concentration of mass dubbed the Great Attractor. But the numbers never quite added up. The gravitational pull of all the visible galaxies we could see in that direction wasn't quite strong enough to explain our tremendous velocity. It was a nagging discrepancy, a cosmic accounting error that hinted at something missing from our models. Some astronomers began to wonder if the problem was not just about what was pulling us, but also what might be times behind times us. Perhaps our motion wasn't just a pull from the front, but also a push from the back. A repulsive force. But gravity as we understand it only attracts, it doesn't push. The only thing that could create the times illusion times of a repulsive force would be a profound and immense absence of matter, a region of space so empty that its lack of gravitational pull would create a differential, effectively pushing, pass away as we are pulled towards denser regions. A faint, unsettling idea began to take hold. Astronomers turned their telescopes around, looking in the direction opposite our motion, a region of the sky dominated by our own galactic plane obscured by dust and stars. They began to peer into the northern celestial hemisphere, into the darkness behind us. Was it possible that our strange, unexplained motion was the first clue? Could it be that our unexceptional address in the cosmos was in fact a lie? Were we the cartographers of the universe living on the very shore of one of those great dark, cosmic voids, and only just now beginning to realize the immensity of the emptiness that has been looming over us all along undefined? And so, with these initial tantalizing glimpses of a universe stitched together with filaments of light, humanity's celestial cartographers faced a new and far more profound challenge. It was a problem of inverted perception. For millennia, we had built our knowledge of the cosmos by searching for things to see, for stars, nebulae, and galaxies. Our telescopes were designed to gather light, our minds trained to find patterns in the brightness. But how do you map what isn't there? How do you chart the shoreline of a sea of nothingness? You cannot take a photograph of an absence. You cannot measure the temperature of a void. It is an object defined solely by what it lacks, a ghostly outline traced by the things that surround it. To truly comprehend the grand architecture of the universe, we had to learn to see the dark. This required a radical shift in technique, a leap beyond the simple two-dimensional portraits of the sky. A photograph, no matter how deep, is fundamentally flat. It can show you where a galaxy is in the sky, but it offers no clue as to its distance. Two galaxies appearing side by side in an image might be genuine cosmic neighbors, or they could be separated by 1 billion light years, one sitting directly behind the other from our perspective. Without that crucial third dimension depth, the true structure of the universe remained a tangled illusion. The cosmic web was a tapestry crumpled into a single sheet. Unraveling it required a key, a cosmic yardstick powerful enough to measure the abyss. That key was hidden not in the brightness of a galaxy, but in the very quality of its light. It was a discovery born from the mind-bending reality that our universe is expanding everywhere all at once. As galaxies are carried away from us on this swelling tide of space-time, the light they emit is stretched along the journey. Just as the pitch of a departing siren drops, the wavelength of this galactic light is shifted towards the lower frequency red end of the spectrum. This phenomenon, the cosmological redshift, became our ultimate tool. The principle was elegantly, beautifully simple. The farther away a galaxy is, the faster it recedes and the more its light is redshifted. Measure the shift and you have measured its distance. Suddenly we had depth perception. The flat photograph could be exploded into a three-dimensional map. Each galaxy was no longer just a pinprick on a celestial sphere. It was a precise coordinate, a point plotted in the vastness of space. Now the real work could begin. Now we could finally start to survey the emptiness. The first major attempts were heroic, almost Herculean labors undertaken in the latter decades of the 20th century. At the Harvard-Smithsonian Center for Astrophysics, a small, dedicated team of astronomers embarked on a project that felt at the time impossibly ambitious. Their goal for the CFA Redshift Survey was to systematically measure the distances to thousands of nearby galaxies. There were no automated robotic arms or supercomputers then. This was painstaking, methodical, human-driven science. Night after night, they would point the telescope at a chosen galaxy, a faint smudge of light barely visible on a photographic plate. The telescope's instruments would gather the galaxy's meager light, spreading it out into its constituent colors, a rainbow spectrum. Within that spectrum lay the telltale absorption lines, dark bands indicating elements within the galaxy's stars shifted inexorably toward the red. The process was excruciatingly slow. Each measurement could take hours of precious telescope time. Then came the analysis, calculating the precise degree of shift and converting it into a distance measured in millions of light years, one galaxy at a time. One data point plotted on a map that was for now mostly blank. Month after month, year after year, the map grew. Each new point was a victory, another piece of the puzzle. From their perch on Earth, the astronomers sliced the sky into sections like peeling an orange and began to fill in the picture. What emerged was staggering, defying all expectation. They saw galaxies were not scattered randomly like dust. Instead, they clumped together in enormous connected structures. They confirmed the existence of the Great Wall, a stupendous filament of galaxies stretching over 500 million light-years. But for every wall they found, for every cluster they mapped, something else began to take shape in the negative space. There were regions where their survey found almost nothing, vast, strangely spherical volumes, where galaxies seemed to be conspicuously, unnervingly absent. These were the first confirmed voids, cosmic deserts of a scale that strained the imagination. The team had proven it was possible. You could indeed chart the emptiness. But their survey, as monumental as it was still just a glimpse of our local neighborhood. It was like mapping a single county and trying to infer the geography of an entire continent. To see the true scale of the voids, to find out if one of them was lurking right on our doorstep, we needed to go bigger. We needed to survey not thousands of galaxies, but hundreds of thousands. We needed a fire hose of data. The turn of the millennium brought a technological revolution that would make such a dream a reality. Two groundbreaking projects, operating on opposite sides of the world, would change the face of cosmology forever. In the mountains of New Mexico, the Sloan Digital Sky Survey, or SDSS, came online. In Australia, the 2DF Galaxy Redshift Survey began its work. These were not just telescopes, they were galaxy mapping machines designed for industrial-scale cosmic cartography. The era of one-by-one measurement was over. At the heart of these new surveys was a marvel of engineering. Instead of a single instrument pointed at a single galaxy, the focal plane of the telescope was fitted with a massive metal plate drilled with hundreds of tiny holes. Each hole corresponded to the exact position of a galaxy or quasar in that particular patch of sky. Then, in a delicate robotic ballet, a team of technicians would painstakingly plug an optical fiber into each hole by hand, a process that could take an entire evening. Each fiber would act as a tiny dedicated pipeline, siphoning the light from its own specific galaxy and feeding it down to a bank of spectrographs below. In a single observation, they could now measure the redshifts of hundreds of objects simultaneously. Later iterations would automate this process, with tiny robots positioning the fibers in minutes. The efficiency skyrocketed. What had taken the pioneers at the CFA a decade to compile these new surveys could achieve in a single night. The universe was now being mapped at a furious pace. The data poured in, a torrent of numbers, a digital flood representing the positions of millions of galaxies. The resulting datasets were colossal, far too vast for any single human mind or even a large team to process visually. The challenge shifted from data acquisition to data interpretation. The new frontier was not at the eyepiece of a telescope, but in the silent, logical world of computer algorithms. Astronomers and computer scientists collaborated to write sophisticated code designed to do what no human could, to sift through this mountain of coordinates and identify the subtle statistical signature of emptiness. These were the first generation of void finders. They were ingenious pieces of software, each with a different philosophy for how to spot a ghost in the machine. Some algorithms worked like bubble finders in a cosmic foam. They would start at a point in a sparse region of the map and attempt to inflate a virtual sphere, expanding it until it bumped into the walls formed by galactic filaments. The largest sphere it could inflate without hitting anything marked the heart of a void. Other algorithms took a different approach, treating the galaxies like particles in a fluid and looking for the gravitational watersheds, the boundaries from which matter flows away, leaving behind an empty basin. They were digital prospectors panning for the absence of gold. They searched for the echo of nothingness in the symphony of data. For years, these algorithms churned through the immense catalogues of the Sloan and 2DF surveys. They mapped void after void, confirming that these empty realms were a fundamental and ubiquitous component of the cosmic web. Most were distant, abstract features of the universe at large. But then, as they focused their search closer to home in the celestial neighborhood right next door to our own Virgo supercluster, the algorithms began to flag something extraordinary. It wasn't just a void, it was a supervoid. A region of underdensity so vast and so profound it dwarfed most of the others they had catalogued, and its location was, to put it mildly, unnerving. It was right there, looming over us in the northern celestial sky. The first results were met with a healthy dose of scientific skepticism. Could it be an artifact of the survey, a blind spot in the data, perhaps a region of the sky obscured by the dust of our own Milky Way, creating a false impression of emptiness beyond? Every possibility had to be checked and rechecked. Teams of astronomers cross-referenced different surveys using infrared and radio telescopes to peer through the galactic dust, ensuring they weren't being fooled. They painstakingly verified the data point by agonizing point, but every test, every new observation came back with the same conclusion. The emptiness was real. It wasn't an illusion. It wasn't a data error. It was a genuine colossal hole in the universe, and we were living on its edge. With the data confirmed, the next challenge was to make it comprehensible. To turn the endless tables of coordinates and redshift values into something the human eye could understand, something we could feel. This is where science became art. Using powerful visualization software, astronomers and data artists began to render these digital points into a tangible reality. They built a three-dimensional model of our corner of the universe, and for the first time we could embark on a journey through it. Imagine you are in a ship capable of traversing millions of light years in seconds. We begin at a familiar place, a single bright spiral galaxy, our Milky Way. As we pull back, we see its companion Andromeda and the handful of dwarf galaxies that make up our local group, a tiny, isolated hamlet of stars. We pull back further, and our local group becomes just one small part of a much larger structure, a sprawling filamentary metropolis of thousands of galaxies, the Virgo supercluster. It's a river of light, a bustling cosmic city. We continue to pull back, and we see that even this immense supercluster is but a single thread in a vaster structure still. The Laniakea supercluster, our home, a celestial continent of 100,000 galaxies, all flowing towards a gravitational center known as the Great Attractor. For a moment, we are surrounded by this incredible tapestry, this interconnected web of light and matter, this lifeblood of the cosmos. It feels like the entire universe is like this, dense, populated, alive, and then the camera turns. It pans away from the glittering filaments of Laniakea towards the northern sky, towards the constellation Boötes, and the light simply stops. The bustling galactic metropolis gives way to an unnerving suburban sparseness, and then to an endless rural darkness. The river of galaxies dries up, the tapestry unravels, leaving nothing but bare black thread. We are now flying into it. The last few lonely galaxies streak past the viewport like the final flickering streetlights at the edge of a city before you plunge into the unlit wilderness of the desert. And then there is nothing, nothing at all. We drift for 50 million light years. Silence. 100 million light years. An oppressive, profound emptiness. 200 million light years. The sheer scale of the desolation becomes a physical presence. You feel it. You feel the isolation. This isn't just empty space between stars. This is an abyss where entire galaxies are missing, hundreds of thousands of them. An area of the universe that should, by all rights, be teeming with light and life and creation, is instead a silent, hollowed-out chasm. This was our first true look at the northern local supervoid. It wasn't just a plot on a graph or a flag in an algorithm anymore. It was a place, a terrifying, awe-inspiring, and impossibly vast place. Its southern boundary presses right up against our own local group. We are not just observers of this cosmic feature, we are its immediate neighbours. We live on the shore of the great cosmic ocean of emptiness. The painstaking work of the surveyors had paid off. The ghost in the machine now had a shape, a size, and a name. The discovery was complete, but in another sense, it was just the beginning. Because confirming the existence of such a monstrous void so intimately close to our own home didn't close a chapter of cosmic inquiry. It ripped the book wide open, unleashing a storm of new and far more troubling questions. Questions that would strike at the very heart of what we thought we knew about gravity, the expansion of the universe, and our own peculiar motion through space. For so long, the pieces had refused to fit. The maps we so painstakingly constructed of our cosmic neighborhood were haunted by a persistent, nagging ghost. There was a phantom in the cosmic machine, an invisible hand tugging and pushing at galaxies, including our own, in ways our models simply could not explain. The data was a collection of whispers from 1,000 different directions, each hinting at something missing, a fundamental error in our accounting of the local universe. We had tallied the gravity of every visible galaxy, every shimmering cluster we could find, and still the numbers came up short. The motion was wrong. The cosmic flow, the majestic river of galaxies in which we swim, was being diverted by a force with no apparent source. It was a maddening, humbling puzzle, a final frontier of cosmic cartography that left astronomers staring at their screens, wrestling with a contradiction that struck at the heart of our understanding. Was there some new physics at play? Some dark, unseen concentration of mass we had failed to detect? The theories were as numerous as the stars, yet none could fully reconcile the strange, anomalous drift of the Milky Way through space. But science is a relentless engine of inquiry. It thrives not on certainty, but on the careful, methodical dismantling of mystery. And the solution, when it finally began to emerge, was not found in adding something new to our cosmic ledger, but in acknowledging what was taken away. The breakthrough did not arrive in a single blinding flash of insight. It was a slow dawning realization, a convergence of evidence from instruments that saw the universe in profoundly different ways. One team, using vast radio telescopes, charted the subtle motions of countless distant galaxies, creating a dynamic map of gravitational currents. Another, probing the cosmos in the invisible light of infrared, pierced through the dusty veil of our own galaxy to catalogue structures that had long remained hidden from view. A third group meticulously analysed the faint residual glow of the Big Bang, the cosmic microwave background, searching for temperature variations that could betray the presence of immense structures or the utter lack of them. Separately, these datasets were powerful but incomplete, like individual musical instruments playing their own solitary tunes. The genius, the moment of epiphany, came when these melodies were woven together. When the redshift surveys that measure galactic recession were overlaid with the velocity maps that trace their peculiar off-stream motions, when the catalogues of visible matter were compared against the cold spots in the universe's baby picture, suddenly the discordant notes resolved into a symphony of profound and unsettling clarity. The ghost in the machine was not a presence but an absence. The invisible hand was not pulling but pushing. The great anomaly that had plagued our models for decades was revealed to be a shadow, a vast underlit chasm in the cosmic web, a region so startlingly deficient in matter that its lack of gravity was warping the space around it. The whispers from the data had not been pointing to a hidden treasure but to a colossal void. Here at last was the definitive confirmation. The mathematical models snapped into focus. The anomalous drift of our local group, that perplexing sideways motion against the overall expansion of the universe, finally had a cause. We were not being pulled toward an unseen mass as the great attractor theory had long suggested. We were in a very real sense being pushed from behind, repelled by the startling emptiness of a region of space so enormous it defied all previous scales. We had been searching for a mountain and discovered instead the most profound valley in our corner of the cosmos. And it had a name, a designation that speaks to its geography, its unnerving intimacy, and its breathtaking scale, the Northern Local Supervoid. Let us break down that name, for each word carries a weight of discovery. Northern simply refers to its location, a vast swath of the cosmos that lies predominantly in the northern celestial hemisphere, from our perspective on Earth, centered in the constellation Boötes. It is a quiet, unassuming patch of sky, one you might glance at on any clear night, never suspecting the abyss that lies beyond its familiar stellar patterns. Then there is local. This is the word that should send a shiver down your spine. This is not some distant, abstract feature of the far-flung universe, a mere curiosity for theorists to ponder. This void is our neighbour. Its edge is shockingly close, cosmically speaking, beginning only a few 100 million light-years away. For context, the observable universe is over 90 billion light-years across. The Northern Local Supervoid isn't just in our universe, it's in our zip code. And finally, the term that captures its true majesty and terror, supervoid. This is not a mere bubble in the cosmic foam. It is a continent of nothingness. Its dimensions are so far beyond human comprehension that we are forced to resort to the abstractions of mathematics and the poetry of light. To journey from one edge of this supervoid to the other, even travelling at the universe's ultimate speed limit, the speed of light would take you more than 500 million years. Imagine that. The dinosaurs rose, ruled the Earth for an epoch, and vanished into history, all in a fraction of the time it would take a single photon to traverse this emptiness. Our own species, Homo sapiens, has existed for a mere sliver of that cosmic crossing time. If you could somehow stand at one end and gaze across the galaxies on the far side, would be so distant that the light reaching your eyes would have begun its journey when complex life on Earth was just beginning to crawl from the oceans. Within its staggering volume, a space that could comfortably contain thousands of galaxies like our own Milky Way, there is almost nothing. The density of matter inside plummets to less than 1/10 of the cosmic average. It is a cosmic desert, a region where the generative seeds of the Big Bang for some reason failed to sprout. The gossamer filaments of the cosmic web, those brilliant rivers of galaxies and dark matter, simply part around it, leaving behind a profound and desolate stillness. The silence here is not just the absence of sound, but the absence of substance. This characterization was the result of a heroic, multi-generational effort of observation. Astronomers used the universe itself as a gravitational lens, measuring how the light from background galaxies was subtly warped by the void's lack of mass, a phenomenon known as the integrated Sachs-Wolf effect. This confirmed its profile not as a perfect sphere, but as an irregular, sprawling emptiness, its borders diffuse and uncertain, like the coastline of a fog-shrouded continent. It is not perfectly empty, of course. A few lonely, forlorn galaxies do wander its desolate expanses, cosmic castaways that are moving far slower than their counterparts in the denser universe, their evolution stunted by the lack of gravitational interaction and fresh gas. They are the galactic equivalent of extremophiles, surviving in an environment hostile to the very processes that build the grand spiral and elliptical cities of stars we see elsewhere. For these isolated star systems, the night sky would be a terrifyingly dark canvas, with the nearest major galactic neighbor so far away as to be an almost imperceptible smudge. They are islands in a sea of non-existence, their placid isolation a stark contrast to our own Milky Way, which is currently engaged in a gravitational dance of death with its neighbor Andromeda. And this brings us to the most profound revelation of all, the one that truly redefines our place in the universe. It is not just the void's existence, but its precise location relative to us. The new definitive maps of the local universe show our home, the small cluster of galaxies we call the local group, in a position that is both breathtaking and deeply unsettling. We are not nestled safely in the middle of a cosmic filament surrounded on all sides by the comforting presence of other galaxies. Instead, the local group is perched precariously on the very edge of this immense abyss. We live on a cosmic coastline. Behind us, stretching out into the universe, lies the Laniakea supercluster, a sprawling, luminous continent of 100,000 galaxies, our greater cosmic home. But in front of us, in the direction of the northern sky, the bottom drops out. The river of galaxies at our back flows toward the great attractor, but it does so only because it is simultaneously flowing away from the great emptiness of the void. We are living on the slope of a gravitational hill, on the shore of a cosmic ocean of nothingness. This discovery is a fundamental rewrite of our cosmic address. For centuries, we have systematically dismantled the idea that we occupy a special place in the universe. Copernicus displaced the Earth from the center of the solar system. Shapley moved our sun from the center of the Milky Way. Hubble revealed that our galaxy was just one of billions. This is the Copernican principle, the idea that we are in a typical non-privileged position. Yet the northern local supervoid challenges this comfortable mediocrity. It turns out we are in a very special place indeed. Our location is analogous to living in a small coastal village at the edge of the Sahara Desert. To us, looking out at the ocean, the dense supercluster, the world seems vibrant and full of life. But if we were to turn around and look inland, we would see an emptiness that stretches to the horizon and beyond, an environment fundamentally different from our own. From our vantage point, the universe is not isotropic. It does not look the same in all directions. One direction is crowded and bright, a dense metropolis of galactic structures. The other is a gaping, underdense wound in the fabric of space-time. This realization has profound psychological and philosophical reverberations. It changes the very picture we have of our home. Imagine standing on a precipice in the dead of night. Behind you are the warm lights of a city full of noise and activity. Before you is a sheer 1,000-foot drop into absolute darkness and silence. That is our home. That is the local group. We are a tiny, fragile island of light, clinging to the edge of a chasm. Our entire galactic neighborhood, with its intricate dance of satellite galaxies and its future collision course with Andromeda, is playing out on a narrow celestial beach with the cosmic surf of the Laniakea supercluster on one side and the unfathomable emptiness of the supervoid on the other. It's a humbling and perhaps even frightening perspective. It implies that our cosmic experience, the very environment that allowed a galaxy like the Milky Way to form and life to evolve within it, might be shaped by this proximity to the abyss. We are not average observers in an average place. We are edge dwellers, shaped by the tension between the great something and the great nothing. This discovery did more than just solve the riddle of our peculiar motion. It opened up an entirely new line of inquiry. By confirming and characterizing this gravitational desert, we were forced to confront its dynamic influence. Emptiness, it turns out, is not passive. A lack of mass creates a lack of gravity, and in the grand cosmic dance, a lack of pulling power is functionally equivalent to a push. Just as a cork in water is pushed up by the pressure of the surrounding liquid, our local group is being gently but relentlessly nudged away from the void by the gravitational pull of the denser regions of the universe behind us. The northern local supervoid is a gravitational repeller. It is an active and powerful agent in the story of our galaxy's journey through space. It is the reason our trajectory is not a simple straight line toward the densest regions like the Shapley supercluster. Our path is a complex curve shaped by the pull of the mountains in front of us and the undeniable push from the immense valley at our back. So the map is finally complete, the ghost in the machine identified not as a monster, but as a vacuum. Yet solving one mystery so often gives birth to another one deeper and more compelling. We now see the void. We understand its scale and we feel its influence. But a new question now hangs in the cosmic silence, a question that shifts our focus from cartography to destiny. Now that we know we live on the edge of the abyss, we are compelled to ask, what does the abyss do to us? How has living on this cosmic shoreline shaped the history of the Milky Way, the formation of our solar system, and perhaps even the trajectory of life itself? The void is no longer just a feature on a map. It is a force of nature, an engine of cosmic change, whose subtle, persistent influence we are only just beginning to comprehend. The great emptiness above us is not just a place, it's a verb, and it is actively shaping our past, our present, and our ultimate future in the cosmos. And so the map is drawn. The great emptiness has a name, a shape, and a staggering scale that defies our terrestrial intuition. But a map does not just tell you where you are, it tells you where you are going. For generations we charted our cosmic motion as a journey times towards times, things pulled by the gravity of Virgo, tugged by the immense Norma cluster, and drawn inexorably toward a mysterious concentration of mass we dubbed the Great Attractor. We saw ourselves as adrift in a cosmic river carried along by the gravitational currents of giants. But with the revelation of the void, this entire picture has been thrown into a profound new light. We now understand that our motion is not just a story of attraction, it is also a story of repulsion. The northern local supervoid, it turns out, is not a passive feature on our celestial chart. It is an active kinetic force, a phantom hand on our backs, shaping our cosmic destiny in ways we are only just beginning to comprehend. This concept feels deeply counterintuitive. How can times nothing, times push? How can an absence of matter exert a force? The answer lies not in a new exotic physics, but in a reappraisal of the cosmic landscape. Imagine space-time not as a flat plane, but as a rolling terrain of hills and valleys sculpted by the mass of galaxies and clusters. The superclusters dense with matter are the great mountains of this cosmic geography, their immense gravity creating deep wells that pull everything towards them. The voids, by contrast, are the vast, shallow valleys. There is no force pushing up from the bottom of the valley floor. Instead, the effect is one of relativity. Standing on the edge of such a colossal depression, you are no longer pulled equally in all directions. The gravitational pull from the dense regions behind you, the cosmic mountains, is now unopposed by a corresponding pull from the emptiness in front of you. It's not so much a push from the void as it is an unmitigated, relentless pull from everything else in the universe. The northern local supervoid is the most significant valley in our immediate vicinity, and we, the local group, are perched right on its slope. This gravitational differential acts like a cosmic watershed, creating a flow, a steady and powerful celestial current away from the underdense region. For billions of years, this subtle but persistent repulsion has been shepherding our galaxy Andromeda and all our smaller cosmic neighbours. It has been clearing out the space around us, helping to define the very edge of the Laniakea supercluster, of which we are a part. It is a cosmic headwind that has been blowing for eons, contributing a significant velocity to our peculiar motion through the universe that is our movement relative to the smooth expansion of space itself. Our journey towards the Great Attractor is not a simple fall. It is a complex dance, choreographed by both the pull of the mountains ahead and the effective push of the valley at our back. We are not merely falling, we are being channeled. This realization has forced astronomers to recalibrate our entire understanding of local cosmic dynamics. The velocities of nearby galaxies, once attributed solely to the gravitational allure of massive structures, now had to be reanalyzed. Suddenly, a new term had to be entered into the equation, the void. This invisible influence accounted for discrepancies that had puzzled scientists for decades. It explained why some galaxies were moving faster than they should, and why the local flow of matter seemed more organized, more directed than models had predicted. It was the missing piece of the puzzle, a force defined not by its presence, but by its profound and influential absence. We live in a universe shaped as much by what isn't there as by what is. The great filaments of the cosmic web, those brilliant highways of galaxies, derive their very definition from the abyssal darkness that surrounds them. The void gives the universe its structure, its texture, its very form, and we are living witnesses to its power perpetually sliding down the gentle cosmic scale gradient away from its heart. Living on this precipice has profound implications. From our vantage point, the universe looks different. When we gaze in one direction towards the teeming heart of the Virgo supercluster, the sky is rich with galaxies, a glittering metropolis of ancient light. But when we turn our telescopes the other way towards the constellations of Boötus and Hercules, we are staring into the facade of the void. The view becomes sparse, the galactic count dropping off precipitously. It is a stark and humbling reminder of our place on the edge of an immense cosmic desert. This proximity might even skew our perception of the universe's fundamental properties. For instance, our local measurement of the Hubble constant, the rate at which the universe is expanding, could be subtly affected by the outflow from the void. Living in a region that is in a sense being stretched out by this gravitational imbalance could make the local expansion appear slightly faster than the cosmic average. We might be living in a special place, a bubble of acceleration, and for years we may have been mistaking a local weather pattern for the global climate of the cosmos. The complications are immense, but so are the opportunities. Our unique position offers a perfect laboratory for studying the interplay between the largest structures in existence. We can observe in real time how a supercluster pulls and a supervoid pushes. We can measure the velocities of galaxies being peeled away from the void's edge and funneled into the gravitational catchment area of nearby clusters. We are watching the cosmic web assemble itself, witnessing the slow, majestic process of structure formation that has been unfolding for 13 billion years. Our home is not a quiet, average suburb in the cosmic city. It is a dynamic shoreline where the tides of gravity, driven by the continents of matter and the oceans of nothingness, are in a constant, dramatic and creative flux. The void is not just a neighbour, it is a co-author of our cosmic story, its emptiness, a silent partner in the grand gravitational dance that dictates our past, our present, and our ultimate future. But what of the void itself? For all its defining emptiness, it is not a perfect vacuum. It is merely underdense, and within its unfathomable volume, against all odds, there are inhabitants, there are galaxies. To find them is to undertake one of the most challenging observational hunts in modern astronomy. It is like searching for a handful of scattered, dimly lit cottages across a continent devoid of cities. These are the void galaxies, the loneliest and most isolated systems in the entire universe. They are the cosmic castaways, adrift in an ocean of profound nothingness, separated from their nearest neighbours by hundreds of millions of light-years of barren space. Their very existence was once a theoretical paradox. According to our primary models of galaxy formation structure, grows hierarchically. Small halos of dark matter merge to form bigger ones, pulling in gas that then ignites with stars. This process is driven by density. It needs proximity. It happens most efficiently in the crowded filaments and bustling intersections of the cosmic web. The void, by its very nature, is an environment hostile to this kind of cosmic community building. So how did they get there? Some may be cosmic flotsam, ejected from denser regions by violent gravitational interactions billions of years ago, flung out into the emptiness like a stone from a sling. Others, however, appear to be true natives of the void, born and raised in this desolate landscape. These are the systems that truly challenge our understanding. For them to have formed at all the initial seeds of density in their small patch of the primordial universe must have been just barely strong enough to collapse and form a galaxy while being too weak to attract anything else. They are galactic soloists, performing a slow, quiet evolution far from the chaotic orchestra of a cluster. Studying them is like opening a time capsule. In the bustling environment of a galaxy cluster, galaxies are constantly colliding, merging, and being stripped of their gas by their neighbours. Their evolutionary paths are messy, violent, and complex, overwritten by countless interactions. They are cosmic cities, rebuilt and remodeled over and over again. Void galaxies, in stark contrast, are pristine. They are cosmic villages that have never seen a tourist. They have experienced few, if any, major mergers since their initial formation. They are celestial fossils preserving a record of what a galaxy becomes when it is left almost entirely alone. When we look at them, we see systems that have been starved of the raw material for growth. Without a steady stream of incoming gas from the cosmic web, their star formation history is often stunted. Many appear as pale, ghostly versions of their more vibrant cousins, their star-making engines having sputtered out billions of years ago, leaving them to fade quietly into the dark. Others show surprising recent bursts of star formation, perhaps triggered by the slow accretion of the tenuous intergalactic gas that whispers through the void, a final gasp of life in an otherwise quiescent existence. Their chemical composition is often different, less enriched with the heavy elements forged in successive generations of stars, because they haven't had the benefit of galactic recycling and merger-driven starbursts. Observing the night sky from a planet within one of these galaxies would be a profoundly unsettling experience. The familiar river of the Milky Way would be absent. The sky, even on the darkest night, would be a near-perfect black, punctuated by the stars of your own small island galaxy. The nearest major galaxy, like our Andromeda, would not be a faint, smudgy presence, but an impossibly dim and distant speck of light, barely visible even with a powerful telescope. You would be utterly quantifiably alone. The grand cosmic web would be a thing of theory, not observation. This profound isolation makes void galaxies invaluable. They are our control group in the grand experiment of cosmic evolution. By comparing their properties, their size, shape, color, and stellar populations to galaxies in dense environments, we can disentangle the effects of nature versus nurture. We can finally determine how much of a galaxy's final form is predetermined by its initial mass, and how much is shaped by its subsequent, often violent life experiences within the cosmic web. The discoveries are already pouring in, and they are filled with nuance and surprise. We are finding that void galaxies are not all the same. Some are old, red, and dead as expected, but others are surprisingly blue and actively forming stars defying our models of gas starvation. They tend to be smaller and less massive, a phenomenon known as cosmic downsizing, suggesting that in the low-density environment of a void, the deck is stacked in favor of dwarf galaxy formation. They often have unusual morphologies with prominent bars and rings that would have been disrupted by mergers in a denser region. They seem to contain a higher fraction of their mass in the form of gas relative to stars hoarding their fuel, because there has been no external event to trigger a frantic burst of star-making. Each one is a unique specimen, a clue to the fundamental physics of galaxy formation in the most extreme and simplified environment the universe has to offer. They are the Rosetta Stones for deciphering the complex story of their more cosmopolitan relatives. Yet even here in the heart of the emptiness, the story becomes more complex, the mystery deeper. The void we are learning is not a featureless expanse. Faint, ghostly filaments of dark matter, far too tenuous to support the kind of galaxy formation we see in the main cosmic web, are thought to crisscross this desolate terrain. Perhaps it is along these gossamer threads that the void galaxies are strung like pearls on an invisible necklace. Perhaps these structures, these whispers of matter in the dark, provided just enough of a gravitational foothold for these lonely systems to form. This presents a new, even more profound complication. Our models of dark matter and its behavior are largely calibrated by observing its effects in dense environments where its gravitational signal is strong. The void offers a new regime in which to test our theories. Does dark matter behave the same way in these incredibly low-density regions? Do these faint filaments match our predictions, or will these celestial ghosts force us to rewrite our understanding of the universe's invisible scaffolding? We began this chapter by confronting the influence of the void on us, its role as a great repeller shaping our cosmic trajectory. But the journey has led us from our own doorstep into the heart of the emptiness itself. We have found that this region is not a sterile nullity, but a subtle and complex ecosystem populated by the hardiest and most isolated of cosmic survivors. These lonely galaxies have become the key witnesses in our investigation of the universe's past. We thought the primary puzzle was the emptiness itself, but now we see the real and perhaps more telling mystery lies with the few solitary inhabitants who call that emptiness home. How did they truly form in such an impoverished land? How have they survived for so long in such profound solitude? And what can these primordial relics, these quiet ghosts of the cosmos, teach us about our own galaxy's violent and crowded youth before the universe was ever truly full? Their silent testimony may hold the answers to the very origins of cosmic structure. And so this colossal chasm, this northern local supervoid, ceases to be just a geographical location on our celestial map. We have traced its ghostly boundaries, a 3 billion light-year expanse of near-total vacancy. We have felt its subtle chill and imprint left upon the most ancient light in the universe, a cold spot in the cosmic microwave background that whispers of an immense gravitational anomaly. But to truly understand this emptiness, we must now move beyond its architecture and ask a far more profound question. Why is it here at all? Why, in a universe born from an infinitely dense point that exploded outwards, would nature conspire to create such a staggering volume of nothing? The answer we have discovered is not that something was removed from this space. The truth is far more unsettling. The void exists because a relentless invisible force is actively pushing the rest of the universe away from it. This is the story of how the greatest emptiness we know became the greatest evidence for the most mysterious entity in cosmology. It is the story of dark energy. To grasp its power, you must first imagine the dawn of time, a universe unimaginably hot and dense, a roiling cauldron of matter and energy. In this primordial soup, two titanic forces were locked in a cosmic duel for the fate of everything. On one side was gravity, the familiar architect of worlds and stars. Gravity is the great gatherer, the force that pulls things together relentlessly, trying to clump matter into ever denser structures. It sought to weave the primordial gas into filaments, to knot those filaments into clusters, and to crush those clusters into galaxies. Its ultimate goal was a universe of tightly bound islands of matter, a connected and coherent cosmic web. But opposing it was another force, a strange intrinsic property of space-time itself. An energy woven into the very fabric of reality, an outward pressure that worked in direct opposition to gravity's pull. In the early universe, when everything was crammed together, gravity had the upper hand. Its influence was overwhelming. Matter dutifully collapsed, forming the first stars and galaxies, and the expansion of the universe initiated by the Big Bang was actually slowing down, held in check by the gravitational brakes of all the mass it contained. For billions of years, gravity was winning. The cosmic web was being woven intricate and dense, but as the universe continued to expand, a tipping point was reached. The galaxies, the clusters, the great walls of matter grew farther and farther apart, and as the density of matter decreased, gravity's influence over these vast intergalactic distances began to wane. Its grip weakened. This was the moment the other force, this dark energy, had been waiting for. Unlike gravity, which weakens with distance, dark energy appears to be constant everywhere. It is a property of space itself. So as more space was created by the expansion, the total amount of this repulsive energy in the universe grew. It was a feedback loop hidden in the cosmic code. More space meant more dark energy, which in turn meant more expansion, creating even more space. About 5 billion years ago, this quiet, persistent pressure finally overwhelmed the fading pull of gravity on the largest scales. The cosmic expansion stopped slowing down. It began to accelerate. The universe's engine, which had been idling for 9 billion years, was now roaring to life, entering a runaway phase of exponential growth. And the northern local supervoid, it is the battlefield where we can see the breathtaking result of this cosmic coup. Voids are not simply holes that were there from the beginning. They are the living, breathing consequence of dark energy's victory. Think of the universe as an ephemeral foam of soap bubbles. The shimmering walls of the bubbles are the filaments of the cosmic web where gravity has managed to shepherd galaxies together, but the voids are the bubbles themselves, the expanding interiors. And dark energy is the air being pumped into them, stretching their walls thinner and pushing them ever farther apart. The northern local supervoid began its life as a tiny, almost imperceptible underdensity in the primordial universe, a region that by sheer cosmic chance had slightly less matter than its surroundings. In the early gravity-dominated era, matter from this region was slowly siphoned away by the gravitational pull of the denser filaments forming around it. The slight emptiness became a little more empty. But when dark energy took control, this gentle process became a violent excavation. The inherent outward push of space-time itself, now the dominant force, began to work on this pre-existing weakness. It grabbed the edges of the void and stretched them. The space inside the void, unburdened by the breaking effect of matter, expanded faster than the space in the denser regions around it. It became a runaway expansion within the expansion. Our supervoid is not a static relic. It is a dynamic, growing structure, actively being carved out of the cosmos by the universe's own accelerating fabric. The galaxies on its edge are not just drifting away from us. They are being pushed, accelerated into the distance by the creation of new space within the void itself. When we stare into that immense darkness, we are witnessing the physical manifestation of the universe's accelerating fate. We are looking at the engine of cosmic expansion laid bare. This realization transforms the void from a mere curiosity into perhaps the most important cosmological laboratory in our entire sky. Because it is so empty, it is also pristine. The complex, chaotic gravitational interactions that define a galactic cluster are almost entirely absent here. This provides us with a unique, clean environment to test the very foundations of physics. For decades, we have relied on Einstein's theory of general relativity to describe gravity, and it has passed every test with flying colors. But all of those tests have been conducted here in our solar system, our galaxy, or in dense clusters, regions packed with matter. What if gravity behaves differently in the profound emptiness of a void? Some alternative theories propose that gravity might be modified on cosmic scales, producing an effect that mimics an accelerating expansion without the need for dark energy. The northern local supervoid is the ultimate testing ground for such radical ideas. By observing the tiny handful of dwarf galaxies that wander through its interior, and by precisely measuring the motion of the galaxies along its edge, we can map the gravitational field across this immense structure. If Einstein is correct, their movements should match our predictions perfectly. But if we find anomalies, galaxies moving too fast or too slow, or in ways that defy our models, it could be the first sign that our understanding of gravity, the bedrock of modern physics, is incomplete. The void, by its very nature, forces us to confront our deepest assumptions. Furthermore, the very structure of the void's edge acts as a probe for that other cosmic mystery, dark matter. The cosmic web, the luminous scaffolding we can see, is believed to be built upon a much larger invisible framework of dark matter. This mysterious substance provides the gravitational anchor that allows galaxies to form and hold together. The sharpness and structure of the boundary of the northern local supervoid, the way the filaments and walls of galaxies encircle the emptiness, is dictated by the properties of dark matter itself. If dark matter particles were hot, meaning they moved at near light speed in the early universe, they would have smeared out the initial structures, leading to thick, fuzzy edges on the voids. But if they were cold, moving slowly, they would have allowed for the formation of tight, intricate structures, resulting in sharper, more defined void boundaries. The incredibly detailed maps we are now creating of the void's perimeter are in effect taking the temperature of dark matter. The emptiness is helping us understand the nature of the invisible substance that constitutes over 80% of the universe's mass. But the most crucial role the supervoid plays is as a direct, powerful tool for interrogating dark energy itself. The very existence of such a large, empty region provides a stringent test for our cosmological models. Our leading model, known as lambda CDM, presupposes a very specific kind of dark energy, a cosmological constant represented by the Greek letter lambda. This is the idea first proposed and then discarded by Einstein, that dark energy is a constant, unchanging energy density, a fundamental property of the vacuum of space. In this model, the amount of dark energy per cubic centimeter of space is always the same yesterday, today, and forever. This model predicts that voids of a certain size should be common, but that voids as colossal as our supervoid should be exceedingly rare, perhaps a 1 in a billion statistical fluke. The fact that we find ourselves living right next to one is suspicious. It could be that we are just fantastically lucky living in the shadow of a cosmic outlier, or it could be a hint that our model is wrong. Perhaps dark energy is not a constant. Perhaps it is something more dynamic, a field that changes over time, an entity some theorists have named quintessence. If quintessence is real, then the strength of dark energy might have been different in the past, or it could change in the future. Such a theory would alter the predicted number and size of supervoids, potentially making behemoths like the one above us far more common. The northern local supervoid, simply by being, poses a direct challenge to our standard model of the cosmos, forcing us to ask, is the engine driving the universe a steady, predictable hum, or is it a fluctuating power source we do not yet comprehend? Remarkably, we can look for the answer within the void itself. Light, as it travels across the universe, is affected by gravity. When a photon of light from a distant galaxy enters a massive supercluster, it gains energy as it falls into the cluster's gravitational well, becoming slightly bluer. As it climbs back out, it loses that same amount of energy, shifting back to its original frequency. The net effect is zero, but something different happens when light crosses a supervoid that is actively growing due to dark energy. Imagine a photon from the early universe entering the northern local supervoid. It falls into the void's shallow gravitational depression, gaining a tiny bit of energy. But during the billions of years the photon spends traversing the void, dark energy has stretched that region of space. The void has become larger and even less dense, its gravitational well shallower. So when the photon climbs back out, it doesn't have to work as hard. It loses less energy than it gained on the way in. The result is a net gain of energy. The light emerges from the void slightly hotter, slightly bluer than when it entered. This phenomenon, a beautiful interplay between general relativity and cosmic expansion, is known as the integrated Sachs-Wolf effect. That subtle chill we see in the cosmic microwave background, the CMB cold spot, is thought to be the opposite effect, a sign that the void is losing energy from the light passing through. But by studying the light from countless individual galaxies and quasars behind the void, we can search for this telltale energy boost. By measuring the precise magnitude of this effect, we are directly measuring the rate at which the void is deepening and expanding. We are directly measuring the strength of dark energy's repulsive force over a 3 billion light-year canvas. This is not theory, this is not simulation. This is a direct observation of dark energy at work, sculpting the universe in real time. The emptiness above us has become a celestial proving ground, a unique arena where gravity, dark matter, and dark energy reveal their interconnected secrets. And in doing so, this vast nothingness offers us something truly extraordinary, a glimpse into the ultimate fate of our universe. The cosmic story, as written by the accelerating expansion, is one of increasing isolation. The same force that is carving out the northern local supervoid is at work everywhere on a cosmic scale. The voids are all growing, merging and pushing the islands of matter, the superclusters of galaxies, farther and farther away from each other. If dark energy is indeed a cosmological constant, this process will continue inexorably. Looking out from our Milky Way in 1 trillion years, an observer would see nothing but our own local group of gravitationally bound galaxies. Every other galaxy, every other cluster, will have been pushed beyond our cosmic horizon, their light receding from us faster than the speed of light itself, rendering them forever invisible and unreachable. The rich, populated tapestry of the cosmos we see today will have vanished, leaving us stranded in an endless, silent void. The universe will become a dark, cold, and profoundly lonely place. This is the Big Freeze, a future where the relentless expansion powered by dark energy erases all structures, cools all stars, and ultimately ends the cosmos, not with a bang, but with a slow, fading whisper. The northern local supervoid is a preview of that final state. It is the future of the universe emerging right next door. When we gaze in its direction past the familiar stars of our own galaxy, we are looking into a premonition. We are seeing the end of cosmic history written in the language of emptiness. The greatest questions we have ever asked. Where did we come from? What is the universe made of? Where is it all going? Find their most potent clues not in the brilliant furnace of a star or the majestic swirl of a galaxy. They are found here in the profound and terrifying beauty of the abyss. An abyss that challenges our models, tests our theories, and reveals the invisible engine that dictates the fate of everything. And as we stand on this precipice on the shore of the greatest ocean of nothingness we have ever known, we are forced to confront the final humbling truth. Our existence is a fleeting exception, a temporary flicker of complexity on the edge of an encroaching eternal emptiness. And so we arrive at the edge of the abyss, the boundary of our own cosmic neighborhood. The veil has been lifted not to reveal a greater concentration of light, but an almost unimaginable expanse of darkness. The journey that began with a subtle nagging anomaly in the cosmic microwave background, a cool patch in the sky, and a puzzling outward motion of our own galaxy has led us here. It has led us to a place we can never visit, yet a place we can never leave. It has led us home to the quiet, cavernous heart of the northern local supervoid. For decades, our cosmic address felt secure, nestled within the bustling Virgo supercluster, a small suburb of a grand celestial metropolis. We saw ourselves as part of a great cosmic web, a luminous tapestry woven from the gravity of 1 trillion galaxies, but the evidence painstakingly gathered from the subtle dance of distant starlight and the faint echo of creation has rewritten our story. The map is irrevocably altered. Our true cosmic address, it turns out, is a far more isolated and humbling place. We are not residents of the great city, but inhabitants of its vast, untamed hinterland. The local group, with our Milky Way and Andromeda as its twin pillars, is not being pulled into the dense heart of the Virgo cluster by its immense gravity alone. We are also being pushed from behind, expelled by a profound absence, a gravitational desert spanning nearly 2 billion light-years. This is the final, startling revelation. Our motion through the universe, the very vector of our cosmic destiny, is shaped as much by what is not there as by what is. This realization forces a radical shift in our perspective, a Copernican-level re-evaluation of our place. We are voyagers on an island of light, the Milky Way, adrift in a silent ocean of near-nothingness. The grand filaments of the cosmic web, those brilliant highways of galactic commerce and creation, are not our home. They are distant shores, shimmering on a horizon we can see but may never reach. Our entire supercluster, the magnificent Laniakea, is itself just a tendril, a peninsula of matter jutting out into this immense void. We live in the cosmic penumbra, where the great structures of the universe begin to fray and dissolve into emptiness. To understand our place is to understand that we are defined by our isolation, and in that understanding we uncover one of the deepest truths of the cosmos. For all of human history, we have sought meaning and presence in substance. We studied the stars, the nebulae, the galaxies, the tangible, luminous objects that populate the heavens. We built our models of creation on the foundation of matter and energy, assuming that the story of the universe was written exclusively in its densest, most brilliant chapters. The northern local supervoid teaches us a different lesson, a lesson written in the language of absence. It demonstrates with breathtaking clarity that the universe is an architecture of both substance and void. The emptiness is not a passive backdrop, it is an active structural component of reality itself. Imagine a grand cathedral. We spend our lives admiring the intricate stonework of the columns, the vibrant colours of the stained glass windows, and the soaring height of the vaulted ceilings. But the cathedral's essence, its ability to inspire awe and hold a congregation, is defined not by the stone, but by the space the stone encloses. The void is that space. It is the celestial architecture that gives shape and form to the cosmic web. The filaments and superclusters are the load-bearing walls and flying buttresses of the universe, but the voids are the great halls, the immense naves, where the true scale of creation can be felt. Without these colossal vacancies, the cosmic web would collapse into a featureless, homogeneous mass. It is the gravitational deficit of the voids, their gentle but relentless anti-gravity push that sculpts the universe, herding galaxies into their filigree patterns and giving the cosmos its sponge-like cellular structure. The absence of matter is as fundamental to the cosmic design as its presence. This truth reverberates through every scale of existence. We see it in the structure of an atom, which is almost entirely empty space, separating a tiny nucleus from its orbiting electrons. We feel it in music, where the silence between the notes is what creates rhythm and melody, giving power and meaning to the sounds themselves. The universe, it seems, is the ultimate composer, using both sound and silence, matter and void, to write its magnificent symphony. Staring into the northern local supervoid, is like listening for the grand silence in that cosmic composition. It is a confrontation with the profound organizing power of nothingness, and it is within this very emptiness that the universe has hidden the clues to its deepest and most persistent mysteries. For here in this vast underdense region, the eternal struggle between cosmic forces plays out in its purest form. Across the universe, gravity, the great gatherer, relentlessly pulls matter together, forging stars, galaxies, and clusters. But it fights against an opposing force, an invisible, inexorable expansion that seeks to drive everything apart. In the dense filaments of the cosmic web, gravity is the undisputed champion. Its overwhelming influence masks the subtle effects of the cosmic expansion. But here inside the void, the tables are turned. With so little matter to provide a gravitational anchor, the cosmic expansion driven by the mysterious force we call dark energy becomes the dominant power. The void is a natural laboratory for studying this enigma. The few lonely galaxies that inhabit the void are like corks bobbing on an unseen current. Their motions are not dictated by the gravitational pull of near neighbors, because they have none. Instead, their trajectories are a pristine record of the influence of dark energy itself. They are being pushed apart by the very fabric of space-time expanding between them. By meticulously tracking these isolated galaxies, by measuring their acceleration away from us and from each other, we can begin to chart the properties of this strange anti-gravitational force. Is dark energy a constant and unchanging cosmological property of space itself, as Einstein first proposed, or does its strength change over cosmic time, waxing or waning like a slow cosmic breath? The answer will determine the ultimate fate of Pata, our universe. If dark energy is a constant, then the expansion will continue to accelerate forever. Galaxies will recede from one another with ever-increasing speed. The great superclusters will dissolve, the filaments will stretch and snap, and the voids will merge and grow until they have consumed almost everything. In this big rip or big freeze, every galaxy, including our own, will become an isolated island universe, cut off from all others, its light never again to reach a neighboring shore. Eventually, even the stars within our galaxy will be pulled apart, then solar systems, planets, and atoms, until the universe becomes a cold, dark, and featureless sea of fundamental particles. But if dark energy weakens over time, a different fate may await us. Gravity could one day reassert its dominance, halting the expansion and pulling the universe back together in a fiery big crunch, a cataclysmic reversal of the Big Bang. The future of reality itself is encoded in the subtle motions of the lonely galaxies adrift in the emptiness above us. To decipher that code, we are building a new generation of cosmic cartographers, instruments of unprecedented power and precision designed to map these dark realms. The Euclid Space Telescope, a collaboration of the European Space Agency, is one such pioneer. It is a detective of the dark, designed to survey billions of galaxies across more than a third of the sky. Its mission is to measure the history of the universe's expansion with exquisite accuracy. By observing how the shapes of distant galaxies are subtly distorted by the gravity of intervening matter, a technique called weak gravitational lensing, Euclid will create a three-dimensional map of the dark matter scaffolding that underpins the cosmic web. This will allow us to see the edges of voids with stunning clarity, to trace their boundaries and measure their growth over billions of years. By seeing how the voids have expanded throughout cosmic history, we are directly measuring the historical strength of dark energy. Following in its wake will be NASA's Nancy Grace Roman Space Telescope, a celestial surveyor with a field of view 100 times larger than that of the Hubble Space Telescope. Roman will conduct a new kind of cosmic census using exploding stars type Ia supernovae as standard candles to measure cosmic distances. By finding these supernovae both inside voids and within dense clusters, it will compare the expansion rate in different cosmic environments. This will provide an independent, powerful test of our theories of dark energy. Roman will also pioneer new techniques for finding the universe's most elusive galaxies, the faint dwarf galaxies that are thought to be the most common type of galaxy in the cosmos. These tiny ethereal collections of stars are incredibly difficult to see, and many are believed to be trapped within the great voids, like lost ships in a fog. Finding them would be a monumental achievement. These ghost galaxies are the ultimate survivors. They have evolved in near total isolation, far from the violent mergers, galactic collisions, and gas-stripping events that shape galaxies in the crowded clusters. They are pristine relics of the early universe cosmic fossils that have been protected from the turmoil of the cosmic web by the serene emptiness of the void. Studying their chemical composition, their star formation histories, and their dark matter content could reveal fundamental truths about how the very first galaxies formed just after the Big Bang. They are time capsules, and the void is their sanctuary. Probing the emptiness is therefore not just about understanding the grand scale of the cosmos, but also about reaching back to its very dawn, to the moment the first stars ignited and the universe began to build the structures we see today. Moreover, these future observations will address another profound puzzle raised by the existence of the northern local supervoid, its connection to the CMB cold spot. Is our void truly large enough and empty enough to account for that anomalous chill in the cosmic dawn, a relic of a gravitational redshift from a supervoid in the line of sight? Or are the two phenomena unrelated, a cosmic coincidence of staggering proportions? Perhaps the cold spot signals something even more exotic, a collision with another bubble universe or evidence of physics beyond our standard model. Only by creating a complete, multi-layered map, combining the cosmic microwave background data with the precise three-dimensional locations of galaxies from missions like Euclid and Roman, can we definitively answer this question. We will superimpose the map of the present-day universe onto the map of its infancy and see if the emptiness of today aligns with the coldness of the past. This is the grand endeavor of 21st century cosmology, to map the unseen. We are moving beyond the age of simply cataloging the light and entering an era of charting the darkness and the emptiness. We are learning to read the subtle gravitational signatures of dark matter and to sense the faint accelerating push of dark energy. We are building the tools to see not just the islands, but the entire ocean. And this quest transforms our relationship with the cosmos. The emptiness is no longer a source of existential dread, the cold, indifferent vacuum of space. It is a canvas of creation, a dynamic and evolving landscape that holds the keys to our origins and our destiny. It is a place of profound scientific beauty, a testament to the elegant and often counterintuitive laws that govern our reality. So, the next time you look up at the night sky, at the familiar constellations and the shimmering river of the Milky Way, remember the invisible context of that view. Remember that you are looking out from the inside of a great emptiness. You are seeing the distant lights of the cosmic shore from a quiet, isolated bay. Our galaxy is not falling through a crowded cosmos, but floating through a vast and serene void, gently nudged on its journey by the absence of things. This knowledge does not diminish us. It does not make us insignificant. Instead, it gives our existence a new and extraordinary context. It tells us that here, on this small rocky world, in this particular spiral arm of this particular galaxy, something truly remarkable has occurred. In one of the quietest, most underpopulated regions of the entire known universe, a pocket of matter became organized. It cooled it, condensed it, sparked with chemistry, and it gave rise to life. And that life, against all odds, evolved a consciousness capable of looking back out into the grand emptiness and beginning to understand its structure, its history, and its laws. We are the universe's way of knowing itself, a localized instance of awareness born from the very substance the void so conspicuously lacks. Our journey, and the journey of science itself, is a testament to the power of curiosity. We began with a simple question: why are we moving that way? And the answer has reshaped our view of everything. It has led us across billions of light years, back to the dawn of time and to the frontiers of physics. It has revealed a cosmos more intricate, more subtle, and more magnificent than we could have ever imagined, a universe built not just of brilliant fire, but of profound and elegant silence. The great emptiness above us is not a void of meaning. It is a source of it, a quiet invitation to continue exploring, to keep asking questions, and to always wonder what lies beyond the next horizon in the heart of the beautiful, dark, and empty spaces.